My name's Madeline Coffrin.
My name is Yev Posnov.
I'm Matthew Schaefer.
And my name is Alexander Paripa.
My name is Alexei Zaigin.
And we're Group 7, and we're doing our project on standardizing resilience zones.
So as many of you may know, California is prone to heavy fire seasons, and a big cause of these is equipment failure on transmission and distribution lines. And so utilities have started doing public safety power shutoffs to avoid these issues. And the effect of that is that customers lose power for a prolonged amount of time, and they lose access to necessary amenities such as pumping their gas, or grocery stores don't have power to provide what they need. So that's what we're trying to address.
Our problem statement is to develop a standard for resilient zones based on a real location, and then generalize it for easier deployment of resilient zones in other locations that are prone to public safety power shutoff events.
Next up, we have the issues at stake, which includes the generator and energy sizing and how they are going to operate, figuring out the different isolation methods and how to verify the status of high energy equipment, as well as resolving power flow related issues and the procedures for re-energizing the resilience zones, as well as reconnecting it back to the grid after a PSPS event. These issues will also include accounting for cold load pickup, solar dropout, and renewable integration into the system.
A safe environment for field workers is very important. We want to make sure we have a remote communication between operators and the troubleshooters at the site. We also want to have a local situational awareness for the field workers. Also, good communication of any outages or re-energization to customers and companies. And we also want to make sure that only underground lines are being energized during a PSPS event.
Equipment sizing and operation is very important and unique in each case. In general, it depends on the type of load, the power factor, peak loads during summer and winter, and the generation capacity should be 20 to 30% above the peak load. For generators, it's also important to consider isynchronous and droop mode operation. Since the switch between these two modes cannot be made seamless, we would have to start resilient zone from a black start.
We will be using reclosers for our project. They will be controlled remotely, and reclosers will be used to isolate a section of the feeder, isolate lines under load, and isolate overhead lines from underground.
To simulate our resilience zone, we built a model in SIME. We used the planned equipment ratings, and we ran power flows to see voltages, currents, and load flow. From the simulation, we saw that the original equipment parameters were not sufficient, and we saw voltage collapse due to motors starting demanding too much reactive power. We tried to increase the generator sizing, but that didn't resolve the issue. But increasing the transformer sizing allowed more reactive power to flow through, and we verified that the system was stable with proper voltages and power flows when all the motors were just running.
From the simulation, we've been able to create a standard model for resilience zones. And through this standard model, we were able to create a zone or a diagram for both islanding and normal operation. So in our islanding diagram, we see that our isolated distribution lines are being fed from the emergency generator, where in normal operation, they're being fed through the overhead transmission lines and out through our distribution.
That pretty much wraps up our project. Hope you enjoyed it.